In this video, we're going to continue and pick up from our previous one, and we're going to focus on elements related to the scientific method, and we'll cover various definitions related to variables, data, as well as examining graphs, or at least the first step of studying graphs. But when we talk about the scientific method is a process in which we generate a research question and we carry out a systematic way of answering that research question by using both inductive reasoning and deductive reasoning. The scientific method is considered to be a systematic and controlled process, a very deliberate process in gathering information and analyzing that information to answer a question. And it does involve a sequence of events. The empirical approach is what will be the focus of this course and is a process where objective data is obtained through direct observation. So when we talk about a study that is empirical in nature, it is a study that obtained firsthand data or even secondary data information to arrive at some particular conclusion. An important element of the scientific method is this concept called control, and control is incorporated in experimental types of studies as a way to not allow certain variables or factors to interfere with the study. And ways to implement control include some techniques that is referred to as randomly assigning cases to different research groups, matching cases in different research groups, or blinding or masking. These terms are used interchangeably with respect to a particular treatment that a group would receive in a study. And that sequential approach in applying the scientific method typically starts with a research question that is often deduced from theory or from a previous research study or a previous line of research that a researcher would narrow down to one question. The researcher, once having that question, will move on to the process of collecting and analyzing information that we refer generally to as data, and that will directly answer the question that was posed by the researcher, and then the findings from the data analysis have to be interpreted, and this is where inductive reasoning is applied, where a very specific finding from a very specific empirical approach will be applied to a much broader group of individuals, and that group is the population from which the sample was obtained. Some of the key elements involved in the scientific method from the perspective of the researcher does include a certain amount of skepticism, open-mindedness, objectivity, understanding the difference between empirical findings and non-empirical research. So there is a line of valuable research that is based on theory or an analytical approach to answering a research question. That would be non-empirical. Even though the scientific method is a very prescribed and systematic process, designing the experiment does involve a degree of creativity, and the final step of communication will allow the very important yet not often done enough step of replication so that others can carry out the same methods and contrast their findings with other findings. So the replication process is very important. And when I think about the scientific method, these quotations from two scientists, this quotation up here at the top right hand corner is from an old 1950s television show, detective show, but quotes from Richard Feynman and Albert Einstein really get to the heart of the scientific method. When we get down to it, to carry out a research study that moves us in the direction of analyzing data, we need to understand the concept of a variable. And a variable is a characteristic or condition that simply varies. It changes, or it has different values for different individuals. I've been talking about this term data, and I've been using the term information interchangeably with data, but the term data is one that will be used much more commonly when we have variables that are assigned numerical values. So when we talk about data, we're referring to measurements or observations. A data set is a collection of those observations. Contrast with data, datum is the singular form of data. Data is plural. And so a datum refers to just one measurement or one single observation from one person or from one case in that research study. Sometimes that is referred to as a score or just simply a raw score. These are scores that have not yet been subjected to any sort of statistical calculations, but they're scores obtained directly from the cases or the research participants in that study. Descriptive statistics are calculations of data, of the information that was gathered for the purpose of summarizing the data into a numerical value that represents the group. And the objective here is to simplify the data and to present it in such a way to describe the characteristics of a particular group. Descriptive statistics by itself does have limited applicability. That doesn't mean that it is not valuable. Descriptive statistics is the first step when analyzing information in the form of numerical values. So although its applicability is somewhat limited, it is still a valuable statistic and the first step statistic that always has to be calculated. But by itself, there's typically no interest in predicting to the population if we stop with descriptive statistics. Once we have our descriptive statistics generated, we can then move on to inferential statistics. And when you see the term inferential, what we're doing here is we are inferring to the population that we don't have direct observations in terms of its entirety, but we have a sample of that population, and from the sample we want to arrive at conclusions. And so inferential statistics are a set of formulas and equations that allow us to make the step from the sample to arriving at generalizations about the population, even though we have not directly observed every element or every case in that population. And naturally, since we don't have observations directly from every element in the population, that leads to something called sampling error that the inferential statistics takes into consideration. And so sampling error is just naturally occurring differences or deviations or discrepancies, those terms are used interchangeably, between a sample statistic and the population parameter. And we'll speak more to this in subsequent videos. Some more variables that need to be defined here include the difference between what's called a discrete variable and a continuous variable. The discrete variable, it's a variable that is quantified, but in terms of the units of quantification, those units cannot be subdivided, and as a result there are gaps in between the possible values in that variable. These variables are classified in whole units or whole numbers, and so do not take on fractions. One example of a discrete variable is what we call a dichotomous variable that we'll define, or just simply categorical variables. A dichotomous variable is a variable measured in a study that can only take on for two possible outcomes. And so these are often responses to surveys, for instance, where a person is asked to answer a question, yes or no, or agree or disagree. If there are only two possible outcomes, that is considered a dichotomous variable. Scores can take on more than two possible outcomes, and so the whole integers such as 0, an observation could be assigned a score of 1, a different observation could be assigned a score of 2, 3, so on and so forth. And so that still meets the classification of being a categorical variable. One example of a categorical variable might be the number of people per household that we would not define in fractional units. So there are 2 people in a household, 3 or 4, but we don't have 3.5. There are many measures that are on a continuous scale, and a continuous scale is a measurement of a variable that can be subdivided, in theory, infinitely. And so in this case, the variable takes a value along a continuum, and so in theory, there are no gaps. And so as I indicated, the infinite number of fractional components only works in theory, but in reality, when carrying out a research study, the continuous variable still is a continuous variable, but is limited by how precise the testing instrument is. 2 more very important definitions before moving on to the next set of lectures here includes the difference between what's called an independent variable and a dependent variable. The independent variable in a research study is that variable that is typically manipulated or under the control of the researcher. Now, the term manipulation is referring to a deliberate element of the research design, where a researcher would randomly put people into different groups. As an example, if we are examining a new drug to treat psychotic episodes, the independent variable in a study like this would be the treatment group. And inside our independent variable, our treatment group, we would define a number of what are called levels. So in this hypothetical scenario, in this study to examine the new drug, we would have one group of individuals that would be assigned to what's called a placebo group. This is a group that receives a treatment that does not have the key medicinal ingredient. But the people in the group may experience a beneficial effect from the psychological effect of thinking that they are actually taking the pill, but the pill does not actually have the medicinal ingredient. A second group of individuals, completely independent of the first group, that we might call the treatment group, are taking the pill that does have the medicinal ingredient, and so we would be able in this study to differentiate the outcome between these two groups, and the only item that differentiates the two groups here is the medicinal ingredient. Now, some studies can actually have more than one independent variable. So in this study, even though there are two groups, this is one independent variable, which is treatment. And because the people are assigned to group 1 or a person is assigned to group 2, these are 2 levels of one independent variable. The dependent variable is often referred to as the outcome variable, and this is what is observed. This is what is quantified. So when we think about the key numerical outcome of a study, we're talking about the dependent variable, what the information we obtain from the cases or the participants in the study. So coming back to our hypothetical study of a new drug to treat psychotic episodes, the dependent variable would be the number of psychotic episodes experienced by patients per week. And so you can see here, this is a quantified variable. Another important element in the research process that lends itself to statistical analysis fall under this general category called non-experimental designs. And a non-experimental design is one where the researcher does not manipulate the elements of the study, but rather makes observations of the inherent characteristics of the people in the research group. These involve what are called explanatory or predictor variables and criterion or response variables. And so these are two separate variables in non-experimental designs that focus on oftentimes either just describing a group or tries to predict an outcome. And the outcome is what we refer to as the criterion or the response variable. To draw a contrast, or rather to draw a comparison to slide number 11, the criterion variable would be analogous to the dependent variable, and the explanatory or predictor variable would be analogous to the independent variable. So this graph here is a scatter plot, and the scatter plot is a very helpful and very revealing type of graph that can give the researcher a pictorial evaluation of any potential pattern that might exist. And in this particular study, the scatter plot illustrates the predictor variable along the x-axis. So when we graph the results of a study, of the information that was collected, the x-axis typically presents the elements of the data of the predictor variable or the independent variable. But in this case, in this particular type of design, it's a predictor variable. And the y-axis will present the criterion variable, because what we're observing in this particular study is the power of the predictor variable in influencing or simply predicting the outcome of the criterion variable. In an experimental study, the y-axis would convey the dependent variable. So if we take a look at this scatter plot, we can clearly see that there is a pattern that emerges, that as the value of the predictor variable goes from left to right, the values get larger and larger. The values of the criterion variable tend to increase as well, but not in a perfect manner. And as we'll examine in subsequent lectures, one way to quantify a scatter plot like this is through what's called the line of best fit. And so what we would do statistically is use a statistical technique called regression analysis to fit a line that best captures the trend or the pattern in these data, that as the predictor variable gets larger, the criterion variable tends to increase directly as well. But as you can see, that there's a great deal of scatter about the line, and that scatter can be quantified. And so that our predictions are not going to be perfect, but our predictions can be made with a certain degree of error or of variability. And one other pattern to note here is that on the low end, or in the lower range of the predictor variable values, here we have our prediction error, but at higher values of the predictor we see relatively greater amount of scatter. And so oftentimes the prediction error across the entire range of the predictor variable will be fairly consistent. Here we're just making an eyeball assessment that as we go from left to right, the amount or the magnitude of the prediction error tends to increase as well. And there are statistical techniques to quantify the magnitude of that increase in the prediction error. So this ends our second video of our Introduction to Statistics unit.